Welcome to this episode of Robert's Creative Chronicles. So today we'll be solving this question, which states that a simply supported beam of 4 meters span is carrying loads as shown in the figure below. This is the figure. Draw shear force and bending moment diagrams for the beam. So before we draw the shear force and bending moment diagram for this beam is a simply supported beam. From these two reactions, it's a simply supported beam. So before we start, we have to find the reactions at A and B. So here will be RA, then here is RB. This is the reaction at A, this is the reaction at B. So now, we will draw the shear force diagram here and the bending moment diagram here. So let's do the calculation here. So now to find this, to find these two reactions, we are going to apply the principle of moment. The principle of moment states that for an object in equilibrium, the total sum of clockwise moment about a point is equal to the total sum of anticlockwise moment about the same point. So let's say we are using point A as our reference point. That means the total sum of clockwise moment about this point must be equal to the total sum of anticlockwise moment about this same point. So let's take moment about A. When we take moment about A, RA times 0. Distance here is 0 for RA. So it's times 0. So RA will go. Then RB times the distance from this point is 4. So it will be RB times 4. This moment is what is an anticlockwise moment because it's moving like this. It wants to move this beam to move in anticlockwise moment. Then all this one that is coming down, it will produce clockwise moment. It wants to move the beam like this. So this is clockwise moment. All these ones are clockwise moment, but this is an anticlockwise moment. This one is an anticlockwise moment. So it's equal to this is the only anticlockwise moment here. But there are two clockwise moments here. This is 4 times the distance here is 1.5. So it's 4 times 1.5 plus this one is a UDL. If you convert this UDL to a point load, you get 2 times the distance here. The distance here is 1.5. 1.5 plus 1.5 is 3. So the distance here is 4 minus 3, which is what? 1. So the UDL, the point load, when we convert it to be 2 times 1, which is 2. So this will be 2 times 1. Then the distance, so when you convert this UDL to a point load, it will act at the center. So now since it's acting at the center, half of 1, which is the distance here, is 0.5. So from here to point A is what? 1.5 plus 0.5, which is what? Is 2. So it will be 2 times 1. So it will be 2 times 1 times 2. This is the moment. So this is now anticlockwise moment is equal to the sum of all the clockwise moment, according to the principle of moment. So this is 4 times 1.5 plus 2 times 2, which is 10. So this will be 4 RB is equals to 10. Then RB is equals to what? 10 over 4, which is equals to what? 2.5. Since a reaction is kilonewton. So this is 2.5 kilonewton. Because all the unit of force is kilonewton. So we have found RB. So if an object is in equilibrium again, the total sum of upward forces must be equal to the total sum of downward forces. So here we'll be using negative sign for downward forces and positive sign for upward forces. So here now, so here will be RA plus RB, which is the upward forces, is equal to the downward forces, which is what? This is 4. You know, when you put negative here, if you take it to the other side, it becomes positive. Likewise here, all the moment of all the forces that are coming down is negative. So let's move. So 4, then this is 2 times 1, which is 2. So 4 plus 2. So downward forces is 6. Then this one now, we have found RB, so it's RA plus 2.5 equals to 6. So RA is equals to 6 minus 2.5. So RA is equals to what? 3.5. So this is 3.5 kilonewton. So we have successfully found RA and RB. Now we can draw the shear force diagram. So first, you project down all the points, all these points A, B, C, D. We're going to project all of them down. So now, for the shear force, we're going to draw a line to serve as the base. So now this is the base for the shear force diagram. So now, RA, you know RA is what? Is 3.5. So we're going to move a distance upward to represent this 3.5 kilonewton. If you wish, you can use a scale to relate your distance, maybe meter or centimeter to kilonewton. But let's do a sketch. So I'm not using any scale here, I'm just using a sketch. So this 3.5 kilonewton, you move any distance. Let's come here. Let's assume this point, the distance. So this distance represents this 3.5 kilonewton. Then, now we have moved up. This reaction RA is 3.5 kilonewton. So we have moved up to represent 3.5 kilonewton in this direction. So now, since there is no road here, so the shear force line will be a horizontal line because there's no road here. This reaction, this road here, 3.5 kilonewton, will be constant here. So it will represent a horizontal line like this until you come here because there's a road here. You see? Then we are going to come down 4 to represent this 4 that is coming down. This 4 kilonewton. So we'll come down like this. Here definitely is what is 3.5. So we have to come below it to show the 4 because 4 is greater than 3.5. Here will be 0.5. So we have to come down here. Since here is 3.5, 0.5 has to be added. So this is our 0.5. So now there's a UDL here between. So now here is what is A, here is C, here is D, and here is B. So you know there is a UDL between C and D. So the shear force line will be an inclined straight line. Because of this UDL, uniformly distributed road, the shear force line is now an inclined straight line. So depending on the road, that's how you get your curves to draw on the shear force and bending moment diagram. So you have to study the curve for each of these roads whether UDL, point load, uniformly varying load, and others. So now this is an inclined straight line, and here the distance we are going to move by is 2 times 1, which is 2 kilonewton. So we are going to move down. We're going to move down from here, from this line. You know there will be a line here, this imaginary line. From this line, we're going to move down 2 kilonewton. So from here to that place will be 2. Then added to here will be 2.5. So it will move down from here 2 kilonewton. Let's imagine this my 2. So this is it. And that means from here to here is 2. From this point to this point is 2. Then here is 0.5 here. Here is what? Here it's 3.5. So you write 3.5. Then now the final one here, since there's no load here, it's a horizontal straight line. So now we'll draw a horizontal straight line. And then we will close the curve. And you can see that this is what is 2.5. And here, automatically, even without starting from here, automatically we have arrived at that 2.5 going up. So this is how you know that your solution is correct. We usually start drawing shear force diagram from this left-hand side. So when you start from the left-hand side and you go, at the end you must always get the answer. If your curve is correct, you must get the reaction at B when you reach here. You must get the reaction at B. So even though you even find RA, you can even use this diagram to find RB. So our calculation is correct. So here is what it is 2.5. Let me just write it 2.5. That's the distance here. Here is 3.5. So now to draw the bending moment diagram, we need, this is the shear force diagram. Let me write it. Here and here is positive. Here, because here is above the Cartesian plane, here is like the x and y axis, whereby above the y axis is positive and below the y axis is negative. So here is negative also, and here is positive. So now let's calculate, let's do the shear force and the bending moment calculation. Shear force diagram. So let's do calculation for the shear force diagram. The calculation now, we will start with FE. FE represents the shear force at A. So now, at this point A, let's calculate the shear force. The shear force is nothing but the reaction, RA, the reaction here, RA, which is what? Is 3.5 kilonewton. That's the shear force at A. So this is the shear force at point A. Now, at point C, FC, the shear force at point C is what? At this point C, you can see that the shear force at this point C will be what? Will be RA minus this 4. So the shear force now is what? RA, this 3.5 minus 4, which is equal to what? This negative 0.5 kilonewton. This is the shear force at point C. Then at D, FD, the shear force at point D is what? It will be You know that, let me show you something. You know that, I'm sure you may be wondering how I got 3.5 minus 4. You know that this 3.5 is an upward force. An upward force, I'm taking positive to represent it, and downward forces, I'm taking it to be negative. So 3.5 is an upward force, which is positive 3.5. Then this 4 kilonewton is coming down. Since it's coming down, it's negative. I assign negative to any force that is coming down, positive to any force that is going up. So, so now this will be positive 3.5 minus 4, which is, see, then the next one, this one, when you convert it to a point load, it becomes 2 times the distance it occupies, which is 1. 2 times 1 is 2 kilonewton. So it will be a downward force coming down. So it will also be negative. So the next one will be what? It will be this one we got, minus 0.5 kilonewton minus 2. So this one is minus 0.5 minus what? 2. So this becomes what? Minus 2.5 kilonewton. No, it's minus 2.5 kilonewton. Then the last one, the shear force at B. The shear force at B now, you know, since there's no load here, there's no load at the top here. So the shear force at D will also be the shear force here. And also check from the diagram, the shear force is 2.5, the magnitude is 2.5. So here also will be negative 2.5 kilonewton. So in simply supported beam, the shear force here will be the shear force here also. And you can even see it. You know that this 2.5 occupies the lower bottom of the y-axis. So it's even negative when you look at this diagram. When you look at this diagram, from this shear force diagram, this one is occupying negative part. So you see negative 2.5. No, that's the logic. I know you may want to think that we'll add it to this 2.5, but if you add it to this 2.5, you will get 0. So that's why it's negative 2.5 kilonewton. So that's it about the shear force. Now let's do the bending moment diagram calculations. So the bending moment at the first point A, you know, theoretically, the bending moment diagram at these two extreme ends of a simply supported beam is always 0. At this point is 0, at this point is 0. So there is no need for calculating, but I will show you. Let me show you. Now, it's like taking moment at this point. The moment at this point will be 3.5. This is RB is 2.5, so it will be 2.5 multiplied by 4. Yes. Then this is what? This is negative 4. So it will be minus. You know, this force is coming down, so it's minus. It also applies a moment. So if you are using a force that is coming down for calculating any moment, you take negative. So it will be negative 4 times the distance here, 1.5. Then minus again. This if you convert it to point load, to be 2 acting here. So it will be 2 times the distance from the middle of this. The distance from the middle of this to this point is 0.5 plus 1.5, which is 2. So it will be 2 times 2. You see 0. So that's why we don't usually calculate. We just take it as 0. Even here, if you find it, the moment at this point is also 0. So that is how you do it in simply supported beam. So here is 0. The next one, C. At point C, at this point C, the moment is RA times 1.5. RA is what? 3.5 times 1.5. So it will be 3.5 times 1.5 is 5.25 kilonewton meter. 5.25 kilonewton meter. So you can also use another, we use this side to find the moment, this left hand side. You can also use the right hand side to find the moment. By, you say this one, but it's longer. There are many forces you need to use here. Here, we only needed to use one force. That's why it's more convenient to find it. It's easier to find it here. But let me show you using here. It will be RB. RB is what? 2.5. 2.5 times what? The distance from here to here is what? Is 2.5. 2.5. 2.5. Then here is 2 times 1 is 2. 2 times. Then here will be 2 times what? Times 0.5. Negative 2 times 0.5. You see, 5.25. So any direction, anywhere you do it from, you still get the same answer. So that's it. Then the third one, MD, is what? We'll just use it easily here. It will be 2.5 times 1.5. You can also use here 2.5 times 1.5. 3.75 kilonewton meter. Oh, this is it. MD. The moment at B also will be 0. So now, you can see from this calculation, the maximum bending moment is 5.25 kilonewton meter. And theoretically, in a simply supported beam, the maximum bending moment occurs where the shear force diagram changes sign. And at the point it changes sign here is C. It changes sign at this point, C. So you can see, and you can see that the maximum bending moment diagram actually occurs at C. So it's correct. So whenever you where any point the shear force diagram changes sign in a simply supported beam, that is where the maximum bending moment diagram occurs. So let's draw the bending moment diagram. So we'll draw this. So now here will be what? Point A. Here will be point C, point D, point B. So now you can see that at this point, A and B is 0, 0 bending moment. So it's 0 here, 0 here. So now at this point now, at C is what? Is 5.25. So we'll come and mark somewhere here to represent 5.25. Then at point D is 3.75. 3.75, it will definitely be lower than the distance we are going to mark here will definitely be lower than 5.25 distance we have marked here. So it will be somewhere maybe here. So it's 3.75. Some people use scale. Maybe you say a scale of 1 kilonewton to 1 centimeter. You can use it. Or you can, but this we are just sketching it. So now, here you can see from this point, since there's no load at this point, there's no load, there's no point load, or there's no UDL. And the shear force diagram is a horizontal straight line. That means at this point also between here, the bending moment diagram will be an inclined straight line. Since there's no load here, the bending moment diagram will be an inclined straight line. So you just draw an inclined straight line here. So this bending moment line will be an inclined straight line. So here again, there's a UDL. So since there's a UDL between these 2 points, C and D, the bending moment line here will be a parabola. That means we'll draw a parabolic curve here. We can use the French curve. So we will do like this. Then now in the same way there, since this point here between D and B, there's no road on top, it will also be an inclined straight line. The bending moment line here will also be an inclined straight line since there's no road here between D and B. And here, since it's occupying the upper part of the y-axis, it is now is positive. So this one, this is the shear force diagram. Should I write it here or here? Let me just write at top. So this is the shear force diagram, and this is the bending moment diagram. So here is the shear force diagram, and here is the bending moment diagram. I hope you understood this episode. If you have any question, feel free to contact me using my WhatsApp or email written in the description below, or you can write them in the comment section. Thank you for watching. Please don't forget to like, share, and subscribe to my channel, and hit the notification bell to get notified as soon as I drop a new video. Thanks.